is a trilogy of 3 over the next 3 days. I hope most of you can follow us along for the ride. And we're going to try to change the format of how we do this. In conjunction with a lot more of the work that we hope my team, the Real World Performance Group, will do over the next coming years in terms of trying to get people to debug and analyze performance problems in a methodical manner. So, I guess the first thing to find out is who we are. Well, I'd like to welcome about a fifth of the Real World Performance Group who are actually up on stage. And today we're actually going to live the life of a Real World Performance Engineer by solving problems as they come to us. And I can't tell you the 3 scenarios we're going to go through today, how many times we have repeated this exercise. Okay? These are real world test cases that have been condensed to get them in an hour. Okay? This is our bread and butter. This is our life. It's probably your life as well, but you may not be attacking the problems the same way we are. Now, my team is a global team. We have people from all over the world. Probably 300 plus man years, and that's not all great experience working on a daily basis. And really, our end game is to increase the performance as you see it. We want you to get better and better database performance in production, in tests, but in the real world. That's our end game. And our methods really sound obvious, but you'll be surprised how many people don't do these things. We use the product as it was designed to be used. That sounds obvious. You'll be surprised. Okay? All the decisions we make, we can back up with numbers. It's a numerical and logical debugging process. It's not using the force. We're not guessing at it. We're not hoping and praying. We're not rolling the dice. We're using numbers to support our assertions. We're going to try and educate as many people as possible how we do it. And really what our big mission is to avoid and eliminating tuning, which is a word I think everybody on this panel hates, because tuning is a bad word. How many people say, I'm going to tune the database? You're not going to tune the database. Now that's done by the guy who wrote the code. What you're going to try and do is allocate resources and make sure you don't run bad code in the database. That's not tuning. So we see that word tuning a lot. And the big thing that drives us crazy is the amount of hacking, guessing, tuning by luck. How many people do it by bit flipping? I found 5 parameters. I'll set one of them higher. Well, that made it go slower, so now I'll set it lower. This we see all the time. Okay, so where can you find us? How many people have looked at our YouTube videos, just out of curiosity? So, homework, assignments, go visit YouTube. There's a number of last year's videos up there on important topics. Also to find us, we're on the road, particularly Tom and Graham and myself. We have a road show that we've been doing for a couple of years now. The next few dates, as you notice, it's pretty much in the southern hemisphere, but we're on the road continually doing these road shows in conjunction with the user group. And if you'd like to see more in your region, let your local user group know, and we'll see what we can arrange. It's a day out, it's a day of painting, it's a bit of fun. Okay? But what we thought we'd do today is we'll do a certain amount of role playing, and today's theme is all about response time. Okay? Because after all, response time is probably your first measure of quality. If it doesn't come back fast enough, you have a performance problem. Okay? It's your first measure of quality. And the other aspect about response time is consistency of performance. Okay? If the response time isn't consistent, what we're going to show is bad things happen. Okay? And really what we're going to try and get people away, if we look at, in terms of response times, in terms of graphs, looking at it in terms of numbers, we have a sort of graph of response time in a good case and a bad case. In a good response time case, you have a clearly defined spike. It's quite close. All the response times are very close together. And you have a very short tail. There's not many long-running transactions. However, in a poor case, you might find you get a double hump. And the response time graph has got a massive long tail, and there may be transactions that don't come back for a long time. Okay? Now, the averages of both of those graphs might be plenty acceptable, but the distribution can lead to bad things. Okay? So in our first case that we're going to actually look at today, this gives me a chance to introduce everybody we've got here. I'm going to play the role of an IT director, and we have a performance problem. And this is a picture that we have onto our war room screens. Okay? What you see here is our war room screens. And at the top, the first two windows are our measures of application performance. We've got a throughput graph, and we've got a response time graph. Below that, we have database wait event graph. Below that, the CPU on the database. Now, what we're going to do is look at this first workload. And what I have here is extremely poor response time. I think it's about 3 seconds. And I was really hoping for response time in milliseconds. And we're only at about 2,000 transactions a second. I was wanting it much higher than that. And so I'm going to ask Bob, my DBA, what his perception of the whole problem is.
Well, if you take a look at the wait events on the graph there, right, we can see that we're using some CPU, but we're not using much CPU. So maybe I think we should just throw more users at it, and that will increase the response time.
So perhaps we should just try throwing more users at it, and it will get better. Would you like to try that?
Yeah, that's a fantastic idea.
Now, we've been having this discussion for months on this system, and we'll see what happens. And it gives me an interest because I'm a very lucky guy today, because one, I've got the development manager who developed these applications, and I have Graham and Robin representing the Real World Performance Group to try and give me a little bit of extra help to figure out what's going on with this performance problem. So, we've doubled up the users. What happened?
It looks like absolutely nothing.
Absolutely nothing. We doubled up the users, and in fact, nothing happened. So you were right. So any more suggestions?
Maybe we should have the Real World Performance team.
Okay, all right. Okay, Real World Performance team. What do you see? You got any ideas what's wrong?
Okay, well, it's kind of tough to see through you. But apart from that, I mean, if we look at that response time, it's running at, what, about three seconds. When we look at the database, it looks like the database is really pretty quiet. It's not really doing very much. So, are we really sure this is a database problem? I mean, it seems like we need to get more data here. So, we have information about the response time. Can we get a breakdown of where that response time is going to that? Right, so the green part there represents the time that's being spent in the app server. And what looks like a red line along the x-axis is actually the database, time spent in the database. So, well, by tuning the database, we could maybe reduce the size of that red line. Does anybody think that would really help the 3-second user response time? Probably not. So, I mean, this certainly looks like it's something that is outside of the database. From a DBA's point of view, it's somebody else's problem.
This is driving me crazy because every day I hear from the application teams it's the database's fault. The database people always blame the hardware. So where is the problem? There's got to be things. So, I understand we put some code changes in last week in the application server to allow us to do more clever caching or something like that.
Well, one thing we can do, can we see how busy the application servers are?
Well, has anyone ever in my team ever looked at how busy the app servers are?
I want to get somebody else to do it. Okay. So those app servers are looking pretty much paid. Right? So that's definitely somebody else's problem.
Now, I'm not the greatest performance expert, but when I see something at 99%, I usually think that's the problem. Would that be a fair assessment?
That would be a fair assessment, yes.
Okay, Tom, is it possible to back out those code changes we put in last week?
They were all performance improvements. It's caching.
I'd just like to see the system without those code changes, if it be possible.
If you insist, we can go back.
Things is changing. You can see fairly quickly where the problem really was. We were spinning in the app server. Okay? How many people have taken a heap as a database problem and never looked how busy the app server was? How many people are running Informatica on the middle tiers? Everyone's looking at their feet now. Okay, and they never looked at the CPU? Oops. Okay, so let's just have a look at this in conclusion. Okay, so let's just conclude. And perhaps Graham or Robin, you'd like to describe the steps you took to make the analysis.
Well, if we look at the analysis, the first thing we wanted to know is we needed more data to be able to determine where the problem actually existed. We could see that the database, as our DBA noted, was not really working very hard. But putting more users in there was not going to create more CPU because those existing users were spending their time in the application server logic. We needed to break up the response time to see what the actual components were of that time. And we needed to focus our attention on places where the most time was being spent. When we looked at the application servers, we could see that they were more than full or fully utilized up to 99%, and that's a very bad symptom as well. Combine that with recent code changes, and that's a good sign that you need to look outside your database and improve the performance there.
Okay, so you can just see grabbing the numbers is the key. Okay, we weren't using the force. The answers were all staring us in the face. But that's just the first problem. I have another problem database, and this has become quite a problem. Database design, and I'm really reluctant to roll it out to a larger user community because for 5 minutes the system performs fantastically and everybody's high-fiving and very happy and proud of themselves. And then for the next 5 minutes, the system performance is appalling. And the impact of this is that all my middle tiers start timing out and I take a full system outage effectively. The system is rendered as good as useless, okay, for this period of time. And we can't explain it, we're really stuck. But perhaps I'll ask the DBA to give an overview of what he thinks the problem is.
Well, again, I guess we need to look at the wait events that are going on. And now we can see we have this log file sync thing. So, a little bit of Google research would lead me to believe that we need to run the log writer in real time.
Run the log writer in real time. Can you explain to me what that is?
Well, I can tell you what Google said about it.
And you read about this via a Google search, is that correct?
I did read about this, yes.
And were they running it in production, what they said they were doing?
Absolutely not.
So you're recommending we do this? Maybe not. Okay. Fortunately, we have help. Okay, we have the real world team. Now, you guys are brand new to my system. You've not seen this before. You're fresh to the system. As you can see, we've got these peaks and valleys in terms of performance and response time. And what we do see is when the red stuff goes up, we get this magnification effect. When the response time from the database is really poor, you can see why our app servers time out, because it magnifies the response time as we go up to the stack. Okay? So a small little response time problem at the database magnifies itself at the app server, and eventually the people out on the other end of this wire gets into trouble. Perhaps you could tell us what you see and what you think.
Well, what we're seeing, although it is a little hard to see, we're seeing some spikes that look like perhaps the I/O system is having to work hard at an interesting interval. And we're noting up there at the top that you've got somewhat reasonable average wait times for your log file events. And yet, as we go through the graph on the side, we're seeing some very long tail outliers. Over in what I think says log file sync.
Yeah, so if you can mouse over the end of the active session chart. So when we see these big spikes, the wait event that we're seeing there is log file sync, which the DBA successfully identified. But if we look at the histogram data that we have, we can see that there's a very big variation in the times that those log file syncs are taking. We've had a number of them that have actually taken over a second, even though the vast majority are going very quick.
Are you telling me that some of the IOs took over a second to just write a few bytes out?
Yeah, well, we don't actually have any log file parallel writes that are over a second, but we have quite a number of them that are between 64 milliseconds and a second. So, yeah, there's some very slow IOs going on here. And one of the issues with log file parallel writes being slow is that it backs up all of the transactions. If you have a really slow log file write, then you're going to get many, many more transactions than normal backed up behind that. So you're going to get a disproportionate number of very long log file syncs. And so if you look at the ratio between the long log file syncs and the long log file parallel writes, you'll see we're running 96 sessions. You'll see it's almost a 100-to-1 ratio. So every time we have a long log write, all of our sessions are backed up behind them.
So you're thinking there's something wrong with the I/O. It's taking a lot of time to do a write, and it's effectively just stalling the whole database.
Right, that's correct.
Interesting. So I've got some numbers to sort of come up with a theory as to what it is. How do we fix it? DBA, what do you think you should do to fix it?
Well, another quick Google search has suggested that maybe we just turn off logging. I found this underscore parameter. We seem to do that.
Again, I ask you, what you read on Google, would people run this in production?
Probably not.
Perhaps the real world team would like to comment on that.
And what is this underscore parameter that you're thinking is that?
Underscore logging.
And how long did you intend to remain a DBA?
Probably get through the next 45 minutes.
So, due to the potential for not just data loss, but also corruption of your database, we strongly recommend that you don't pursue this option. Don't even.
I can see why that could be a career limiting maneuver. Okay, so we've eliminated suggestion number 1 on the basis it will get us all fired. Any other suggestions?
Well, there is something called asynchronous logging. And that will allow us to batch up our commits and then write the redo in an asynchronous fashion. And that's a little bit of a better solution. It's supported and it's not underscored.
So you mean it's a better solution in that you don't get a physically corrupt database, just a logically correct database. That's an unusual definition of net.
Less bad.
Right. Anyway, I think we turned that on.
Well, turn that on for your benefit. Bearing in mind what the real world team has just told me, I'm now getting a bit concerned about the system that's now running in production with asynchronous logging turned on. And we can see that there's something going on my system because there's this sawtooth effect. And, well, perhaps this asynchronous logging thing has got some merits to it because I'm not getting those big dips anymore, am I? But I'm getting a whole lot of pink. Perhaps the real world team would like to tell us what the pink is all about.
Well, Kaya, can someone give me a clue what the picture
So is that the log buffer space?
That's the log buffer space.
Oh, the log buffer space, yes, that would be a side effect of the change that you just made.
I can fix that one.
That's right. Yeah, so basically we've removed one bottleneck, and so now all of the sessions that we're trying to do their log writes, now they're just bottlenecking in a different place. Essentially, so we just move the bottle. I mean, that's something that we see every time we go through looking at a system. We remove one bottleneck and you're on to the next one. In this case, we're certainly getting more throughput, but how do you feel about the potential for logical corruption?
I'm very uncomfortable about this decision, and Kaya, if you could please turn this async logging off as quickly as possible so I can remain in a job. That would be much appreciated. So, we're kind of stuck here at this point. Okay, perhaps the real world team can actually start asking some more questions and give some ideas as to how do we solve this problem in the real world?
Well, you've got a few options for how to solve this problem. The first thing we might want to, or we need to understand, is where this other workload is coming from. We want to find out what it is that's running on the I/O system that is causing the spike in the reading log or the reading files, reading log things. We might find that this is a required workload and there's a good reason for it to be running, or we might find that it is something that has been kicked off in the background. Maybe there's a new process that shouldn't actually be running on the server and this could be eliminated. We might also find that we need to separate out some of the different workloads because we did consolidate on the server, as I understand it. And then a secondary option would be to separate the log files onto their own disks and make sure that
because we were seeing very long log writes.
Right.
Now, if this is on a shared corporate SAN with all of the other workloads that are going on from consolidated databases, we can get, if there's a lot of work on the other databases, we can get very slow IOs. That's not a good thing for the log file writes. So one option might be to have dedicated disk writes to the logs. Now, sometimes folks say, oh, right, log files, so we need SSDs for those. Actually, as long as you have dedicated drives for those, you're doing pretty well. You're going to get most of the benefit, necessarily the SSDs, but splitting it from the rest of the workload that's on your IO system.
So this is running on state-of-the-art Exadata system, and I'm still having these IO problems. I don't understand.
Well, if you're on Exadata, then you have something that is called flash logging that should be enabled and would take care of this issue because it would smooth the impact of the additional I/O. It gives you what it does is you have your log that writes to disk, you have your log that writes to flash cache, and one of them is going to be fast enough to make sure that you can service the system well. So, do you have flash cache?
I think it got turned on 15 seconds ago.
It is.
Yes.
That's a very good thing.
Okay, so I would like to know why it wasn't turned on earlier.
Well, I was doing some testing and I wanted to turn it on so I could blog about it.
As you can see, we've now turned on flash logging. Perhaps Graham and Robin, you'd like to comment on what we're seeing now, apart from that really straight line and that response time being extremely red.
Yeah, so we're getting flat response times down at ellipse of 1, and we're getting flat throughput for the transactions through the database. And we still see some peaks in the activity on the database when this workload or the other systems comes in. We're also seeing that there's more blue in there, so that the IO, that's because our IOs are getting slower during those periods because of the other IO that's being done by the other workloads. So, but we've improved the throughput, and you still have a database that is consistent and that you can recover, which is probably a good thing.
So let's just conclude as to what we learned here. There was a problem outside the database again. We'd actually been hammering the I/O in the background workload. Now, how many people run databases on shared SANs? Because they get disk space allocated by space. And the DBA, or the storage administrator, has striped everything over everything. And then every hour on the hour, your Microsoft Exchange server synchronizes. And suddenly you get this unexplained log file sync showing up at the top of the hour. Who many people have lived that in their life? Okay? You see how sensitive a small response time deviation of things, like a simple thing like a log I/O, can be reflected all the way to the top of the application stack. When you build a multi-tier architecture, it's a very loosely coupled system. Everybody's waiting on each other. So we saw that magnification effect. Perhaps Graham or Robert, you'd like to go through what you saw at a database level as if you were going to write a report.
Okay, so basically the key thing was that during the core performance times, we were seeing lots of these outliers in log file parallel write, which was leading to a much bigger number of outliers in log file syncs. So that was down to high-low level storage subsystem. So what we did was introduce the flash logging in this case, which took those outliers out of the system and gave us more consistent log file parallel write times, and therefore more consistent log file sync times. We'd also probably put in the report that if this was a non-Exadata system, you'd probably want to put the logs out onto dedicated drives. And the other thing to do, of course, is to look into the background workload and see if that's really essential, if there's anything that can be done to tune that to make it less intrusive.
Okay. So you can see reading logging quite a simple one. Now, I have a third database for analysis. Okay. Now, we've been really lost with this one. It's an existing application that used to work really well. But what we had to do is put a hook in the code to start logging all the clicking analysis that was going through the system, so we could get a big table so we could start doing analysis on a later point in time. And every time this one row of insert, it seems to bring the whole system to a halt. And that's what I've been told. Perhaps the DBA, perhaps you could give us an idea of what you think is going on.
Okay, well, let's have a look at what's going on in the system again. Let's see what our red stuff is. And we're seeing buffer busy waits and index contention. So this must be because of the index that we have on our logging table. So what I think we should do is rebuild the index with a different mini-trans and a different percent free, so that we can get a smaller number of rows in the index box and we'll have less contention.
Interesting idea. Any other ideas?
Maybe we can have a smaller block size.
Really? Interesting concepts.
So rebuilding the index, how long do you think that's going to help for? Because do you realise that because the PCT3 on your index is only ever used when you create the index, not during normal maintenance, like normal activity on the database, like inserting a row into the index. That doesn't obey the PCT3, so your blocks are going to get filled up anyway. So unless you're intending rebuilding the index every couple of days, maybe, to get that percent free, and that's maybe not the best idea, since it's not going to be online when you do that, I don't think.
Okay, so we've got the situation where there was index contention, and I believe our development manager had an idea as to how to solve that problem.
This is actually an index on the sequence populated field.
That's correct, yeah.
If I put it in number 1, and the number 2, and the number 3, and so they're all going right next to each other. So top right-hand side index. And I read this book. The book, it tells me that I can take that index, and I can reverse the bytes in the key. And so it's called a reverse key index. And so instead of 1 going next to 2, next to 3, I'm going to put 1 over here, and 2 might be way far away from it. 3 is going to be far away from it, and so on. And so what it's going to do is, instead of inserting into this top right-hand side block, that's our buffer busy width, that's our index contention, 100%, it's going to spread the inserts out across the entire base of the index. So when I go to insert the sequence, I'm going to put it in the left-hand side. When you insert the next one, it'll go on the right, and then branch this one, it'll go into the middle. No more hot block. Buffer busy weights will go away, and the index engine contention is going to disappear as well.
Well, we just built one and put it in place. Want to comment on it? We certainly seem to have got a jump in the transaction rate, and the response time has come down quite dramatically. That seems a pretty good idea. You know, brilliant idea. And I think we're back to being off-file sync bound because we're committing all the time. Well, that's excellent. Real-world performance team, would you like to say what you think about the suggestion? It looks good to me.
Yeah, it looks like a definite improvement. I mean, we're getting more than twice the throughput here. How big is this table that we're inserting into at present?
I think we populated it from empty.
Yes, it's pretty small.
Okay. So,
I was going to ask you, this index is useful? Do we need to do range scans or anything like that on this?
No, it's always
I would look at using a reverse key for
So as this table grows, we're concerned about the performance being able to be sustainable. We think we're going to start to see some I/O problems, probably any second. Amazing how fast it takes.
Yeah, so having the reverse key index, it's almost the same. One entry is inserted on the left-hand side, next entry on the right-hand side. They're spread evenly across the entire size of the index. That's fine when it's all in cache. Once you get to that index being larger than cache, each of those entries that you're trying to put into the index becomes a disk read. And that's what we're seeing now. All that blue is we're having to read blocks from disk so that we can put an index entry into it.
You guys are starting to scare me.
Right.
Because you're trying to tell me that as the application runs, it's going to get slower than it was before.
Right, and had we spoken about this fast enough, we would have been able to see that with the reverse key index on a large table, we've now, by replacing the buffer busy weights with disk IOs, our throughput has actually fallen. Right, so we put the reverse key index in to try and improve the throughput. Once the object got big, it actually made performance worse than it was before.
But you don't have any more buffer busy weights.
Yeah, those 2 millisecond buffer busy weights have been replaced by 5 millisecond cell reads. Yeah. Okay. That's performance tuning.
So I don't think we have a sustainable solution here, do we, at all? I'd like to open it up to the real world performance. What would they suggest as a means to get me the performance I had when that table was little?
Well, we've already heard from the development manager that we don't need to be concerned about range scans. And we're not running on a rack system, so a very good option in this situation with the large table is going to be to hash partition this index, which is going to give us a distribution over the hash partition keys. Similar to what Tom was describing in avoiding the hot locks earlier.
Yeah, so instead of going from one hot, bright-growing index block to having lots of cold blocks, the entire size of the index, we're now having a small number of warm blocks which each stay in cache, and we don't need to do an I/O for all of our inserts. So having a hash partition index, we get the best of both worlds, and kind of that.
Well, it's appeared to have got the response time back to where it was, and the throughput back up to where it was.
Right, and this is with a large table we're doing this rather
So
than small.
I'm feeling better about this application now. It's starting to meet its performance goals and objectives that we set out to do with. But because whilst we've all been debugging this, I got a text. My goals have changed. We've just bought another company and now we need to double it. How are we doing with this? I've heard that we can do some clustering and run in a rack cluster. So will this solution work in a rack cluster?
You're not going to get as good of a performance impact from, you will start to see the contention for the index return when you add in the node, and the contention will come from the GC weights.
So we're doing about 2,000
Yeah, can we try this on a rack system?
It might be good to give it a try.
Yeah, so we're doing about 10,000 transactions a second on a single node. And we just started enabling it in the cluster with 2 nodes. I'm not seeing anywhere near 20,000 transactions a second. There's something wrong with software or hardware. I don't know what's going on here. There just must be something wrong.
And how many nodes is your targeting now? You're saying that
We were hoping to
your
go
target changed.
We were hoping to go up to 4 because this application is probably going to go global. So we're recognizing that we probably need to go to about 4 nodes.
Right, so if going from 1 to 2 is getting you maybe 25 to 30%, probably going to get reduced benefit as you go to more nodes. So maybe we need to look at a different option for.
Yeah, I also noticed we're back to response time hell as well. You know, what we did was shift the work over 2 nodes. The response times got worse, and I'm not even seeing the same throughput. You know, there's got to be something wrong here.
Well, if you look at the weight events that are now showing up in the database, we're going to see that they've changed. So now we're seeing that we have the index contention weights, but we also see the GC weights, which are caused by putting the information about in between the rack clusters.
So to improve the performance of this, really what we're trying to do is get rid of those GC events. Right? So that's going to give us much better performance on cluster. And one way to do that is to come up with, rather than just using the raw sequence that Oracle gives us, to actually prefix that sequence with information that gives us locality. So for example, sticking the instance ID that we're doing the insert into this weblog from onto the front of the sequence before we insert it into the log table. And in fact, we can take it a step further than that and make sure we don't contend across sessions by putting the instance ID and the session ID. And so then we still have, because we're not running that many sessions, we still have a relatively small number of insert points into the index, but there's never any chance of any contention. And we're going to completely get rid of those GC weights because we're never having to ping blocks across the cluster.
So I'm not using partitioning. The only thing we did was change a line of code. Tommy, you cool with that?
We'll have to regression test it.
change the line of code up top by just changing the way the numbers get generated. And by being smart about how we generate the numbers, we can stop people fighting with each other. And you made the grey go away. Is that correct?
That is correct.
And so response times come down again.
And we're up at about 20,000 transactions a second, which conveniently was twice what we had with one node. Okay, so you can see that a lot of this stuff, when we get back to it, you can see, just to summarize all of this, index contention, usually on inserts, are both problems single instance and multi-instance. Okay, and the old wives' tales will only get you so far. Okay, because you have to recognize where you are. The first solution, you saw that to be an exceptionally good solution for a while the table was small. Very good solution. Okay? Until such point that the index became so big, it became bigger than your buffer cache. Okay? And then you had to start doing physical IOs to get it in there. The hash partitioning solution was extremely good because it focused all the insert points into a few pages in memory. So that was really good. Because if you're doing all the inserts in memory, you're not incurring an IO, things are going to run fast. And if you're taking down the contention level, it's likely to scale up. But when you move into a cluster with a hash partition index solution, what's the chance of finding the block you want to find in your own local cache? Well, with 2 nodes, it's 1 and 2. When you go to 3 nodes, it's 1 and 3. As you add nodes, your batting average gets reduced all the time. So by having clever sequence generation, you can ensure that you always find where you want to insert in your local buffer cache, and hence get that insert statement to scale. Okay, and we've even given you up the sort of sequence structure, which is you want to append the instance ID with the session ID with the actual sequence that you've used to generate uniqueness. Okay? Big problem that we face all the time. You have to change the line of code to get the optimal solution. Okay? The answer is always in the code. People just don't want to hear it half the time. Okay, but what we really tried to show with these 3 examples is that response time is a great indicator of performance and also gives you a clue as to what's really going on. I think we've got some graphs here, and you'll notice there's a correlation between throughput and response time for the same workload. When the response time is high, you'll notice the response time is low. Funny that. Okay? In the times when the response time is high, you're not actually doing anything, you're spending your whole time waiting to fight for resources. Okay? This is pretty much the basics of OLTP debugging all your life. Okay? You know, finding out where the time went, we did that in exercise number 1. Go where the biggest wage was. The second exercise, okay, look for the erratic performance. Look for the outliers. Don't get dumbed down by averages. Okay. Third one, internal database contention. Learn how to eliminate it and mitigate it with all the various tools. It's all out there for you. That's the simple solution. It's what we do, believe it or not, every day. These things even get escalated all the way through support. All our services still are arriving at our desk. And the first thing we ask is, could you tell us what the I/O outliers are? It's all there in the system statistics. Now, master of system statistics, Graham, do you want to give us some points? The numbers are there in the histograms and stuff available to you?
Yeah, I mean the histograms which were introduced in 10. Did you say the event histograms? Yeah, event histograms really are a very good source of information to get you beyond looking at averages. If you looked at the averages for the log file syncs and the log file parallel writes in our log file scenario, you can see that the averages look pretty good. And often that's what you hear from the SAN administrator. Oh, there's no problem with the I/O subsystem, right? Our averages are great. Well, but it's not the averages that cause you the problems, it's the outliers. So looking a little bit deeper than just the averages and looking at those histograms really can give you a very good start on identifying problems.
On that point, the last one we've got, you can see your DBA options and developer options to eliminate some, well, probably the most common form of contention altogether. It's all there, out there. Please go home and play it. Now, the tracing that we're running on War Room scripts, can we just get back to that? This is, we've developed this as we're going to be using this a lot all week as an education console. Unfortunately, we can't give it to you, but we are intending to make up more YouTubes and take it on the road so you can show it to your boss's boss, your boss's boss's boss, to make the point with all the issues that you're seeing. And if you like this format, please let us know, because we're just starting to sort of try and show a worked example of every problem we see, have it reproducible in front of you so that people can develop a library of learning. If you like it, please let us know. And at the end, I'd like to thank Robin and Graham and the Real World team, Tom, Bob, who is actually a really good real world performance engineer, and Kaya, who really is the star of the show because he wrote all of this stuff, and he deserves a round of applause in his own right.